In this session, we're going to talk about chemical reactions. And just real simply, a chemical reaction is two substances or even one substance. You're starting with a couple of substances and they have certain properties and they're going to react together. We call them reactants. They react together and they form different substances.
You can't have one substance have a chemical reaction with itself.
Oh, yeah.
You can?
You can. It's a type of reaction that we're going to talk about. Yes, we can. And the important thing, we know it's a chemical reaction because the products, what's made from the reaction, have totally different properties than what you started with. And you can't go back, right? So speaking of that, yes, you can. You can have one reactant that forms several different products. There's a lot of types of reactions that we could talk about. Mm-hmm. We're going to talk about 4 basic types of reactions. And I like to start with these 4 because they follow really definite patterns that students are going to be able to see really, they make it really concrete for the students. And that kind of sets them up then to learn about more complicated reactions as they go further in their science courses. The first reaction we call synthesis reaction, or sometimes you'll see it referred to as a composition reaction. And we're going to show you just the pattern for this reaction. Then we have the opposite of a synthesis reaction, which gets to your question. That's called decomposition. And that's where you start with literally one reactant and it breaks down to form maybe 2 products, maybe 3 products. It can get, it can really break it down to form any number of products. Then we have a single replacement reaction where one reactant is replaced by another, one of the reactants to form 2 different products. Sometimes you'll see those referred to as single displacement. And then we also have a double replacement reaction or double displacement reaction. And that's where 2 of the reactants sort of switch places and form 2 brand new products. But how do we know? Like, how can we visually see that a chemical reaction has taken place? And there's like 4 indicators that would tell you that possibly a chemical reaction has taken place. And one of those is a temperature change. Now, a temperature change is not always going to indicate that a chemical reaction has taken place, but many times it goes with other indicators of a chemical reaction.
And that's with any of the 4. Mm-hmm. Just because you see one happen doesn't mean there's a chemical reaction.
Correct.
They're indicators of.
Yes. Okay. So that's one thing is, was there a temperature change? Maybe the temperature increases, which I think a lot of times we just expect. If there's a temperature change, it gets warmer. But you also have to consider that there are reactions where the temperature drops. So if you think about a cold pack, if a kid falls and they go to the nurse, maybe they don't have ice, but they might have one of those cold packs that you pop and it gets real, almost kind of icy, and so you can use that.
So which one is, I know endothermic and exothermic, which is which?
Exothermic, the heat is exiting the system, so you're going to feel that heat. Endothermic, the heat is going into the system, and so it's leaving, so it's going to feel cold because that heat is going in.
Perfect.
Okay. Another indicator of a chemical change is the formation of a precipitate, or I guess an indicator of a chemical reaction is the formation of a precipitate. And this can be, I think this is so cool when this happens because you can start with 2 completely aqueous solutions. They could even look like 2 completely clear liquids, and they react together and they could either form a solid precipitate where you see this solid substance form, or sometimes you form my favorite, which is a gelatinous precipitate. And that is just what it sounds like. It kind of looks like a jelly and there was nothing before, but then they react together and that forms it. So that's really interesting to see it when this happens. Examples of those that you would see in real life include a wastewater treatment. So we think about all the impurities and pollution in water, and we run it through that wastewater treatment plant. So you might have a lot of ions, for example, maybe some lead that you don't want in there. And the wastewater treatment companies are going to add other chemicals in that will form these precipitates. Those will settle to the bottom, and then they can run the solution, all that's above it, through other filters, and then that comes out as pretty clean water. Okay. I know you had talked about another type of real-life example for precipitation reactions.
With metals. With metals. I know they get the ore, they crush the ore, and then they put it in vats and they add chemicals to it for chemical reactions to take place, and it will break down.
Probably purified.
It break down, isolates a particular metal.
Yeah.
And then that actually, they'll change the density of the solution. It bubbles up, they pull it off.
Ooh.
The top.
I love how you talk. We'll get back to the bubbles that form here in a minute, because that's another indicator. But another example of a precipitation reaction in the body that happens could be the formation of kidney stones. So calcium ions that you might have in your body react with oxalic acid, which is found in a lot of foods that we eat. And when those two react, that's where you'll get your kidney stones from, which is not a good thing. But that, again, it's just an example of a precipitation.
Is gas
Okay, so gas, I like how you're talking about bubbles and how you're bringing up gas, which is another awesome thing. And I think middle school students especially always appreciate when you can bring up the subject of gas. But that is another indicator of a chemical reaction that's taken place. Digesting your lunch is a chemical reaction. We know this, right? It looks different coming out than how it looked going in. And so the production of a gas or effervescence is an indicator of a chemical reaction. And I think, also, a lot of times if a chemical reaction has taken place, we might see a color change. And a color change, a lot of times, will pair with a change in pH. And we can see changes in pH, we can observe these color changes with indicators. So an indicator like universal indicator. If we add some universal indicator to some just tap water, it's going to appear green. We're going to see this green color because that's where it is around a neutral, a pH of 7. If we take a straw and blow into the tap water for about a minute, we're going to see that it's going to start turning yellow because the carbon dioxide that we're adding to that water is reacting with the water to form carbonic acid. And this is an example of a let's see, the carbon dioxide and the water is forming carbonic acid, which is a synthesis reaction. That's an example of a synthesis reaction. We could also see this happening a little more drastically if we put phenolphthalein. It's a different indicator. We can put this into water along with some dilute base like sodium hydroxide and do the same thing. Make sure you're blowing carbon dioxide into the solution and not ingesting any of the solution. You certainly don't want to drink anything with a strong base in it like sodium hydroxide. But again, you're going to see this color change happen. The phenolphthalein turns a pretty bright, vivid pink at a pH of about 8.2 and above. And once we start producing that carbonic acid, the carbon dioxide that we're adding to the water makes that carbonic acid. That acid drops the pH, and once you drop the pH below about 8.2, it just turns clear almost immediately. Mm-hmm. So again, that color change, a change in pH, and we know that this is indicating that a chemical reaction has occurred.
Perfect. What do we have here?
What we have here is we're going to show a couple of different reactions happening. And one really fun reaction, a lot of students are familiar with this, is the reaction of baking soda and vinegar. Mm-hmm. And we can show this a couple of different ways. I like to use a ratio of about 1 part baking soda to 3 parts vinegar. We're going to see if that works to give us a pretty good reaction. We're going to show that this is well, we're just going to look for some indicators that the chemical reaction has taken place. So if I turn on my scale, and then the other thing is we're going to put on our safety glasses once we get the chemicals out, and I just snapped my safety glasses. I have my safety glasses on. Stephen has his safety glasses on. We've set our scale. We're going to measure out about 1 gram of baking soda. We've zeroed it. You can use a cupcake paper. You could use just a scrap sheet of paper if you, like to recycle. And there we go. I'm going to add in my baking soda. I want about a 1 part baking soda to 3 parts vinegar. It's about 10 grams of baking soda. What I'd like to do with this is I'd like to funnel it into a balloon. You want to try to, I'm going to measure out 30 milliliters of vinegar. I'm going to go ahead and put the vinegar in this really large test tube that we found. And in the meantime, Stephen is adding the baking soda into a balloon. We're going to attach the balloon to the top of this so that we create a closed system. We're going to let the baking soda Oh, magical. So let's look for indicators that a chemical reaction is taking place. We know that the vinegar, before the reaction takes place, it's clear, it's a liquid. The baking soda is powdery and it's white. And we know right away something's happening because the balloon is filling.
Yes. And
we see the
temperature
bubbles.
change.
Oh, and what is this temperature change? What would you think the temperature change might be? And I always like doing this with students. They have really, a lot of times, definite ideas of what they think the temperature change is going to be. And I want to say that sometimes it's surprising what it actually is.
Yeah, because it's cooler.
It does. Yeah,
it feels cool.
It's an endothermic reaction. It does get colder, and so that's always shocks the students a little bit. So not only we had a temperature change, it's accompanied by the production of a gas, which is just awesome. It's fun when you can see, when you can work with gases in the classroom. It's tricky to do sometimes, but again, that 1 to 3, about 10 grams of baking soda to 30 milliliters of vinegar is going to be just about right for using a small balloon with a large test tube like this.
All right.
All right.
What do I do with this?
Well, we're going to set this aside. When we're talking about chemical reactions, it's really good to bring up the point that matter is always conserved and that mass is always conserved. That mass is never created or destroyed. It's only transformed in a chemical reaction. That can get a little confusing to the young student when they see, especially with our baking soda and vinegar reaction, there's still a little bit of the baking soda left here. But if you found the right ratio and you got it just right so that all of the baking soda reacted with all of the vinegar, you would just see a clear liquid in this gas. To the students that are new to these physical changes and these chemical changes, they might think that all the baking soda just disappeared, when really it transformed into a different substance. We want students to understand this, and so we have this modeling activity to show this conservation of mass. This is going to be a great exercise for students to visualize the particulate nature of mass, that the mass that we're starting with in the reactants is completely used in the products that are forming, and that we're not forgetting anything, that nothing's disappearing, and that everything is moving from the reactants to the products. You may or may not have worked with balancing chemical reactions yet, but we sort of take that part out of it. It's already balanced for you, so we can really just focus on all of the reactants changing into all of the products. That they're reforming the products, so they're going to look different as well. So again, those properties that we start with as the reactants, they're going to look different. They're going to have different properties as products. And again, that's all the markers of that a chemical reaction has occurred. Also, visualizing the particulate nature of matter is very helpful to students, especially if they can be exposed at an early age. It's going to help prepare them better for their advanced science classes that are coming. So what Stephen is doing, Stephen's looking at this double replacement reaction that we just did. Reacting baking soda and vinegar is actually a pretty complicated reaction. It's a two-part reaction, and the first part is the baking soda and vinegar reacting, and one of the products of this is carbonic acid. And so what Stephen's doing is he's putting this first reactant, this NaHCO3. So he's using poker chips, and we see that we have one of each of them, and perfect.
Did I do it right?
You did it perfect, yep. And we're going to move all these away so that we're just focusing on this. Here's what we have for our reactants. This is what just happened in this test tube with this balloon. So we want students to look at these, look at how these are arranged.
Which is which?
The NaHCO3, this is the baking soda.
Okay.
This HC2H3O2, this is the vinegar.
All right.
All right. Now what we want to do is we want to have the students use these chips and reform the products.
So what did it make?
So it's making this NaC2H3O2, and we would call that sodium acetate. And then another product is our carbonic acid, this H2CO3. So we see...
Where's the gas?
Where's the gas? The gas, so this is where it's a complicated reaction. This is the first reaction that's happening when we mix the baking soda with the vinegar, is we get this sodium acetate and carbonic acid.
Okay.
Now, carbonic acid is, well, the first I would just want to point out, we definitely see they're rearranged. We definitely use all the poker chips from the reactants. They all made the products in this first step. So matter or mass was conserved in our chemical reaction.
It's balanced.
It's balanced. The second reaction that's happening in this system when we mix baking soda and vinegar, the carbonic acid is really unstable, and the carbonic acid wants to decompose. And so we're going to make let's see here. Yeah, I think it's on the back of this one. So carbonic acid wants to decompose, and so we're going to get rid of all of these chips now, and we're going to look just at the carbonic acid that formed. So that's what's filling up our balloon, this H2CO3.
Can we put little names on these so we know what they are?
Yeah, we can.
I think that would help me.
Okay. Yeah, we can definitely do that. So here's our carbonic acid. This is, again, that's that second part of the reaction. You don't really see the two separate reactions happening. We just see the balloon fills up. But what happens is this carbonic acid decomposes to form water and our carbon dioxide.
You're hurrying me. I gotta make sure they're right.
And so this is definitely different from our one reactant that we had, and now we've got our two products. So this CO2 is what's filling up our balloon. And again, that's the baking soda vinegar. It's a really fun reaction to do, but it's also sort of complicated just because you do have these two reactions in one that are happening.
All right, so this has the CO2's up here.
CO2's up here.
And down here is water.
We have water
and
sodium
whatever this
acetate.
was.
Sodium acetate.
Sodium acetate. Mm-hmm. Okay, that's what's in there.
That's
those
what's in here.
Two things.
Yes.
Okay.
Mm-hmm. So all of this stuff. This is our whole system now in this.
Right.
Okay.
That makes sense.
Good. We can do baking soda and vinegar with baggies as well. Here you can see we've added baking soda to one baggie, and it's white, it's powdery. We can make those observations beforehand. We're going to pour some vinegar into a second baggie. And then to be able to see some other indicators of chemical reaction, we can add an indicator like bromethymol blue. We add a few drops of that. We see that it's green. We add it to the vinegar. Now it's this yellow color. We kind of mix it all up. I'm going to squeeze all the air out of that and then put it in with the baggie with the baking soda. And then again, make sure as much of that air is out of the bag as possible. We can have our students observe how these look before they react. And then we can move them around in the baggie to get them to react. You can see, yeah, all those bubbles forming. Oh my. You can really feel that temperature change. Oh, there we go. Now we're seeing this color change. I was just being impatient. You can see this nice blue as the pH changes as well. So we see a lot of indicators of chemical change happening within this bag. This bag's about to explode. We feel the cold temperature. We can see all of that gas that's been produced, and we can also see the color change from that yellow initially with the vinegar now to a blue where the baking soda had been added. In this session, we talked about several chemical indicators, such as bromethymol blue, universal indicator, phenolphthalein, but a lot of foods can also work as natural indicators. Different foods, like what we see in this chart, have anthocyanins, which respond to pH changes by changing color. So we can see that red cabbage, for example, will be red towards the acidic side of the pH scale, and as we go more basic, we'll turn blue and then down to yellow by the time we get to the basic side of the pH scale.